In this topic, you'll learn about the concept of particle stability and the factors that affect it. This knowledge will help you explain the principle of particle stability while offering coagulant and flocculant chemical products. After completing this topic, you will be able to describe the principle of particle stability in the context of water treatment programs. In nature, particles suspended in a fluid medium are often stable. Milk is a good example of stable colloidal particles. The particle of milk solids and fats are stable in the fluid medium and did not separate even if milk is kept standing for long hours. On the other hand, particulates in muddy water are not stable. Mud particles settle down in muddy water quickly and form a layer of mud at the bottom and clear water on top. As in milk, most contaminants in wastewater are in a colloidal state and are stable. They can't be easily separated from wastewater. However, by altering particle stability, you can agglomerate particulate matter during wastewater treatment and separate them from the wastewater for removal. The illustration displays lemon juice being added to milk. Notice how the milk curdles. If you destabilize the colloid particles in wastewater, you can remove contaminants easily. Solids remain suspended in water for long periods because of electrostatic repulsion and their sizes. Most particles in water exhibit a net negative surface charge. When the surface of a particle is charged, ions of opposite charge become attached to the surface. Electrostatics and van der Waals forces strongly bind these ions to the surface. These excess ions near the surface of particles results in an electrical potential difference. This causes the particles to remain suspended in water due to mutual repulsion. Electrostatic repulsion is the mechanism that controls particle stability. The development of electrostatic repulsion involves surface charge and van der Waals forces of attraction. Surface charges on hydrophilic surface may originate from a variety of sources, such as the dissociation of inorganic groups such as hydroxyl or carboxyl group on particle surface, replacement of negative silicon atoms by a positive aluminum ion resulting in a reduction of the net negative charge on the surface, and the absorption of negatively charged polymer such as fulvic acid molecule onto the positively charged calcium carbonate. At the interface of hydrophobic surfaces, excess anions or cations may accumulate. With hydrophilic surfaces, surface charges exist and it attracts ions of the opposite charge of the surface. The electrostatic and van der Waals forces strongly bind these ions to the surface. The layer of accumulated ions at the surface produces an electrical potential, zeta potential, that repels particles from each other and causes the particles to remain suspended in water due to mutual repulsion. So, the negative surface charge together with van der Waals force of attraction develops a layer of ions next to the particle surface and builds an electrical potential, which prevents particles from agglomerating into larger particles. This completes the topic of particle stability. Here is the summary of the key points. We now have reached the end of particle stability topic in the wastewater treatment series. Thank you for listening and watching this lecture. If you would like to see other courses, please visit watertreatment.training.